Hi everybody, I hope all is well. I'm looking up here at the camera now because I kind of have it above me shooting down at the bench so you can see kind of everything here. And as you can see, this is going to be an interesting video. And what I did was I made an improved version of the Transistor curve tracer to make it a little neater for one thing, and to improve some of the problems that the thing had, to kind of make it more reliable and more accurate. Now the reason I'm doing this little preface clip here at the beginning of the video is that what this project started out as and what it ended up as were two different things. And I'm very happy with the way this turned out, but I did change some of the things along the way. Make sure you watch the whole video. I don't know how long this thing's going to be. It's probably going to be a longer video. Make sure you watch it all if you plan on trying to build something similar to this yourself. A couple of things, and that is that number one, I was going to originally, where did it go? Leave space on here for this little thing that I found this kit online. It's a dual channel oscilloscope, and it was a kit that you build. And I thought, the one thing it could do that a lot of these little cheapy kits can't do is XY mode, which would be perfect for a little curve tracer. Unfortunately, the sample rate and the display on this just wasn't good enough. It's just too pixelated. You could make out the traces, but it's just too pixelated. Everything else I tried it on, any other scope I had, it looked beautiful. So this ended up being a little bit of a bust. Because of that, I changed a few of the things in the design. The other thing I was going to do was put an inverter circuit in there so that when you check a PNP versus an NPN transistor, that it would flip the waveform. But then I realized, well, why do I really need that? Because you can just invert the waveforms on your scope with the push of a button. So that was unnecessary. Now, a couple changes I did do and I stuck with, we'll see in the video as we go along. But if the clips kind of jump around and everything, I'm going to do my best to edit this thing so it makes sense and is kind of linear. But I definitely will have to go back and reshoot some of the clips so they apply to the final product here, so everything makes sense in the end. So hopefully this will turn out good. Hopefully it'll be a fun video, and hopefully we all will get to learn how a curve tracer works. It really doesn't matter if this thing is as good as my Tektronix 577 as I hit this light here. It's not. It's never going to be. But believe it or not, this is a usable piece of test equipment when it's done, and you can use it to match small signal transistors and so forth. But more importantly, you can learn how a curve tracer works. All the principles of a transistor and semiconductor curve tracer are contained in this little thing. So even though it won't be as accurate and doesn't have as much versatility as a big, expensive curve tracer, it's simple so that you can understand it. And that's what this is really all about, is understanding how this stuff works. So I hope you enjoy it, and let's get on with the video. All right, we can now discuss what we're going to do with this little kit, or with all these parts. What I'm going to do is, I ordered another one of these curve tracer kits. Now you've seen me do this. I built one, and you've seen me use it multiple times on videos, but I actually did a video on a DIY curve tracer kit that you can purchase. They sell these on eBay. I think they sell them on AliExpress, and they also sell them, I've seen them on Amazon. If you order one, they seem to take a really long time to come in, so you're not going to get it in a couple days. It took me a number of weeks to get this kit in. And I ordered the one with the optional power supply board. I also had this transformer, and it's 18 volts at 3 amps, so it's more than enough for what we need. It's nice and compact. And I had one of these slope front instrument cases. So these are all things other than this and the scope that I had laying around. The other thing I found was one of these little project boards with pre-spaced mounting holes, and it's just the right size to hold 2 of these zero insertion force sockets. So what I'm going to do is I'm going to make these 2 different test sockets for the test transistors that we're going to use. And then what I'm going to do is put a switch in here so you can toggle, so we can compare one transistor to the other without having to the problem with the first version that I built was it used those little hook clips, and you had to move the clip over to the other transistor to test it, and you're handling the transistors and they're heating up from your fingers. So this is going to be a lot nicer. It's just going to be right here. I can put 2 in at a time, let them stabilize, and then toggle a switch between the 2. Hopefully, if it works. And then this scope, if I did it right, I should be able to just Velcro it or stick it right to the front here, and I'll have a little set of jumpers that'll go here onto the jacks, and those jacks can actually go to a big scope if I decide I want to do that. But this will be like an all-in-one self-contained curve tracer with 2 different power levels, one for, it's a little higher current steps, and one for lower current. Now, it's not going to work like a full-sized curve tracer. We discussed that before, but it does have enough current to actually put a little bit of drive to the transistors to test them, to make a little more sense. So let me get building, and I'm not going to go through the process of building this. If you want to go back through the last video, this is the same board. There's no difference. So I went through the entire process of building these on that video for the curve tracer. Go back and watch that, and when I come back, I'll have this all assembled. Okay, let's look at this little curve tracer kit's schematic and see if we can figure out how it works, and then identify some of the places maybe we can improve on it, and also try to compare this to a real curve tracer, some of the similarities that it has and some of the differences. Okay, now the first thing that I'm going to want to do here, before we go ahead and start on the schematics, I'm going to put this up here. You can do a pause the screen and print to screen and paste this into Paint Shop or something like that. Take a screen capture, and that you'll at least have the schematic for this. To my understanding, whoever's making these little kits, number one, it takes a month to 2 months to get it, if you get it, and second of all, getting documentation from them is difficult. At least so I've read in some comments and some of the reviews on this thing. I have the actual schematic. This is it. You can go to their website, I guess. What is it? TieKits.com, I guess. Some of this stuff, a picture is worth 1,000 words, and when we get this thing all assembled, I'll kind of mock it up on the bench, and we're going to take measurements with the oscilloscope to look at the waveforms. But this is broken into what I'm going to say is 3 different sections. You have an oscillator over here, and that oscillator is going to be somewhere, I think this thing oscillates somewhere around 600, 650 hertz, something like that. It's a low frequency oscillator. And it generates a triangle wave, and they're using that as like a ramp signal. That's feeding into this push-pull circuit. This is an amplifier, isn't it? If you look, you have a NPN and a PNP complementary pair, and they're being driven by this TL074 op amp. So this is your kind of preamp driver section and everything. And that's all there. It's just a very simple amplifier circuit. You have positive and negative 15 volts on the collectors, and whatever this oscillator is outputting, it's being passed straight out to the X jack. This goes to the X input of your scope. You're going to put your scope in XY mode, and it's also connected up here, and you can see it goes into the collector. See there? So you're actually putting into pin 3, which is the collector. So you're ramping up your collector voltage is what you're doing. You're just putting a ramped voltage signal onto the collector. And since it's alternating current, because this has a positive and negative supply, regardless of whether you have a NPN or PNP transistor, the voltage will be in the correct polarity. It's just going to use the positive half cycle for an NPN transistor and the negative half cycle for the PNP transistor. That's really all. So you have your oscillator and you have your ramp driver. And then up here, these are your current sources. And it's pretty cool how they do this. And I want to take some measurements because I'm not sure how they index this. So we're going to look on the scope. But essentially, they're using a combination of things. They're using these 1N4148s as a kind of a constant voltage drop. And then they're using these resistors. So you see, for the low power, which is small transistor mode, they're using these 100K resistors. So there's two in series, which means 200K for this line. One resistor, which is just 100,000 ohms for this line. And then 200Ks in parallel for a 50,000 ohm or 50K in this line. And this is a counter chip right here. And you can see there's your clock. Your clock is being driven by that ramp signal, by the oscillator at the 600 hertz or whatever. And it just steps through these different pulses or through these different gates. And they're using positive and negative 6.2 volts. So you have a differential of what, 12.4 volts between the negative and the ground and the VCC. And essentially what it's doing is it's outputting the voltage, which is going to be however many volts, what is it, 6 volts or something, to these pins. And it steps through that each time the clock goes through. So each time you have a clock pulse, it'll step to the next output. So you're selecting these different current sources. Now, you have to understand how this works, you kind of have to understand what's going on this end. Ignore these switches here, because these allow you to select between the high set of current sources and the low set of current sources. So at one time, you're either going to be using this set or this set, depending on which switch, which way you have it switched. And these go through little relays that are controlled by the jumpers or the toggle switches you put in. If you look at this device under test jack, this goes out and it goes into your base. So this is providing those microamps of base current or milliamps of base current if you're in the high power mode. And that is the base to emitter current. So if you look at the emitter output, that goes down here and that goes to the Y jack of your scope. So that's going to be your amplitude. This is going to control the position of the trace right to left. So this is going to actually give you your sweep. And this is going to give you your amplitude of the signal, okay, for your current. And if you look, there's a 1 ohm resistor going to ground. Now, let's just pretend that we short the base and emitter together, okay? Essentially, by putting the transistor in there, that's like putting a diode between the base and the emitter. You're going to have a voltage drop of a diode drop, which is going to be like 0.6, 0.7 volts, whatever. But if we just ignore that for a minute, if we shorted the base to the emitter here, you would have your voltage right here going through whichever of these resistors is being selected at the moment. It would go through one voltage drop, and it depends on if it's a PNP or an NPN, whether it's a positive or negative voltage based upon this sweep and all that. And that's going to get dropped across this 1 ohm resistor. So you've got a voltage divider between the resistor, the steering diode, and the resistors up here. So essentially what you're going to get is minus the voltage drop of this diode and minus the voltage drop of the base emitter junction. You're going to have a voltage divider between the resistors and the 1 ohm resistor, and this is where you're getting, this 1 ohm resistor is where you're getting the scale of 1 millivolt equals 1 milliamp, because it's a 1 ohm resistor. It's Ohm's law. That's what they're doing right here. Now this resistor doesn't look very important, but it's everything in this circuit, because this is the reference that you're testing across for your to measure your collector current. And if you go over to a real curve tracer, and let me zoom in here. One thing I've not gotten used to is this zoom. Sometimes it's fast, sometimes it's slow on this new camera. But anyway, if you look over here, there's this knob. There's two knobs here. One of them is called max peak volts. The other is called max peak power in watts. And if you look down here, you have this thing called series resistors. Right now, the minimum one on this unit is 15 ohms. You see that? And you can see the little white pointer is pointing to that. And if I pull this knob out and rotate it, I can change the maximum of the series resistors in there. See down here? It's like it's a voltage divider. So these resistors are changing the load. It's that 1 ohm resistor, but you can change the load between this, and this ensures that you don't exceed a certain wattage. If you set these correctly and you know the maximum parameters of the transistor, you can set it so that you can't exceed the maximum spec of the transistor. That's what this is all about. So in a big power transistor, you could put a big load on it, low resistance, high current, and drive that transistor to high current. In a small signal transistor, you have your max peak power on this 100 milliwatts right now. See that right there? The most power you can get is 100 milliwatts. That's really important. And it also gives you a lot of flexibility of the range. So it would be kind of like being able to adjust this resistor and these resistors to kind of change your current sources and so forth. And then you also have a constant current supply that is much more complicated than just this, a voltage drop across a resistor and a diode. It's very specifically adjustable for the steps. So the step generator and everything on that is way more complicated than this and much more versatile. But you have the basic building blocks of that curve tracer in this little circuit, just more limited. So anyway, I hope that explains how this thing works. Now, here's some of the limitations that we have. First of all, let's assume that, you have 6 volts, and let's just assume that you can get the maximum voltage and you can saturate that transistor because of the gain of it. Okay, that's not always going to happen, but let's say we allow the full 15 volts to get dumped through the base collector junction or collector emitter junction and across this resistor. In pretty short order, you can cook things because that resistor is a tiny little thing. It's only like a half watt or a 1 watt resistor. And really, in theory, if you go through all of this, you're probably not going to get more than 1 volt of a drop across this because of the way this whole circuit is designed. It's kind of made that way. And so 1 volt across 1 ohm is going to be 1 amp and 1 watt. Okay? And putting 1 watt across a half watt resistor is probably not going to be very good. So one place we want to do here is we want this to be an extremely accurate resistor. It has to be precision, so we want this to be like 0.1%. Number 2, I want to make this like a 2 watt resistor so that it never gets overheated, even if you have a transistor that somehow has a high gain and you put it in power transistor mode, you're pushing that half watt resistor, and we don't want that. So we want to upgrade this. That's the first thing I want to do. Now another thing I found is these connectors. Where we connect the transistor, I have those banana plugs and I have 3 hook leads that connect to the transistor, much like, you know, the Peak Atlas that we looked at. And that kind of, with this whole thing, that opens the door to having some noise. And so we definitely want to make a better connection for our transistor. The other thing is this has one connector for one transistor. If you notice a lot of these higher end units, looking right here, you can put 2 transistors and you can shift between left, off, and right. See that? So I can take it out of circuit, I can go to left, or I can go to right. And that's really good because if you want to compare 2 transistors to match them, instead of having to unplug and plug a bunch of transistors, you can put your one reference in there, stick this one in, and then toggle back and forth, and you can actually compare the traces. Now, if you look at my Madel one, or Madel, however you pronounce it, the other curve tracer I have, it actually has an electronic switch that will toggle every sweep, every other sweep in between the 2 transistors, and it'll overlay the 2 traces on top of one another. Now, this one doesn't have that feature, but the other one I have does have that. This thing, you can also measure things like the step generator. You can actually look at it on a scope directly. I can go on and on and on how many features this has that the real basic ones don't. So I want a better connector here, and I want to be able to have 2 devices switching. So that's another improvement I want to make. Looking at the supply for the current source, they're taking your plus and minus 15 volts that's coming off of this power supply. This is a very basic linear power supply. It just has a couple of 78, 15, 79, 15 voltage regulators. You have a basic bridge rectifier 1N4002, which is a 1 amp maximum diode. So really, this power supply cannot exceed 1 amp. I have a 3 amp transformer I'm going to use, but the power supply is 1 amp. So we don't want to exceed that, or we're going to overtax this power supply. So you have plus and minus 15 volts regulated coming into the board. It goes through these 1K current limiting resistors. And then you have these 1N, 3234s. These are 6.2 volt Zener diodes, and they're half watt. This is the world's biggest no-no. You do not put 2 diodes in parallel like this, Zener diodes. Let's say that this one, whichever one has the lower Zener voltage, is the one that's going to turn on and keep the other one from turning on. So this really does, they did this for extra power handling, but really, let's say this one, the actual Zener voltage, because they're not perfect, you'd have to perfectly match these. Let's say the Zener voltage on this one is 6.18, and let's say the Zener voltage on this one is 6.21. This diode will start to conduct at this voltage. Since we're not at the Zener voltage of this one will not conduct. As this one conducts, it's going to take the whole load of that current that you're trying to clamp to 6.18 volts. As you do that, this will begin to heat up. As it heats up, this voltage will drop even further, taking it even further away from this voltage. So this one will never do anything. And you're going to overheat this one, and this voltage is no longer regulated. It's moving all over the place. So we want to eliminate that. Now, the ultimate would be to put a linear regulator, like one of those 78s, but they do not make a 78 6.2. They just don't. So you're going to have, I'm just going to use a better quality Zener diode, a 1 watt. I'm going to mount the diode, so I'm going to go to 1 watt Zener, a single. So we're going to do a single 1 watt Zener diode. All right. And we're going to mount it off the board because that diode is rated at 1 watts, including the leads. The leads are really thick on a 1 watt Zener diode. So we want to mount it, you know, a fairly high distance above the board to use a good portion of those leads, because those leads act as heat sinks and they help dissipate that heat. So we're going to go to a single diode, 1 watt, and get it off the board and use the lead length. That's going to ensure that this stays a lot more stable. Now the next thing I want to do is down here where we have this X and Y output. The Y output is very tiny. If you remember from that page, I have another copy of it here, you can have signals that are in the milliamps of output. You know, down here we're talking usually less than 200 milliamps. As a result, you're going to have to put your scope into a very sensitive range, you know, 5 millivolts per division, 10 millivolts per division. Oscilloscopes are notoriously noisy at that level. So you're going to have input noise that you're going to have to deal with. The higher the volts per division you can set, the higher above the noise floor the sensitivity of that scope is going to be operating in. So what I want to do is I want to take this and I want to change that scale. Now there's a couple ways to do it. You could raise this resistor, but that's going to cause all kinds of issues. We don't want to do that because we actually want to keep the load the same. So what I'm going to do is I am going to put a scaling circuit of times 10. That way, when we connect our scope, instead of 1 volt equals 1 mA or 1 milliamp, we're going to have 1 volt equals 10 milliamp or 10 milliamps. So what that's going to do is allow us to move our scale up 1 notch on our scope, you know, by a factor of 10. And it's going to hopefully clean up that signal. You notice when we were in high power mode and I had to change the scaling of the scope, that trace got a lot clearer and had a lot less of those, you know, pixelated looking lines. And we were able to see the trace a lot more clearly. So those are our improvements. Fix the power supply, 2 device switching, and change the scale on this and change this to a high accuracy, higher wattage load resistor, and see how much better we can make the new version work. Now for a case, I am using this one, which I had. I've got a few of these, I forget where and when, but these are made by Bud Industries, and I'll put this on here if you want to look at the actual part number and so forth. It's a PC11495 by Bud Industries, and you should be able to find these online, even like eBay and places should have them. And the nice thing about it is it's a slope front cabinet. It has a front face plate that's aluminum, and I'm going to put the connectors in there and the switches, and then down here will be the business area where we're going to actually have the device under test and an area to set the oscilloscope and just to attach it there. And then at the output, I'm going to have BNC jacks, and then we're just going to use a little pigtail cables to go from that into the input of this, and then we can remove this anytime we want and plug a big scope to it if we want to look at it with a big oscilloscope. So that's my convoluted plan. Let me get the drill out and do the part that I don't like, which is all the machining. And once I get everything mounted, we'll be able to test it out. Okay, I mostly have this thing put together, and as you can see, I have some test probes connected up. 4 of them to be exact, because we have a 4-channel scope. Let's use all of our channels. So these first 3 probes right here are looking at the output of this counter. So they're looking at pins 9, 11, and 12, because those are the 3 that we're using. We're going to see what those waveforms look like. Then I have the 4th probe connected right here to the X to look at our ramp signal or our triangle wave signal. And we're going to look at the timing of them, how they all work. Okay, so the first thing we're looking at is pin 9 on the counter chip, And you can see it's just, all it is a square wave, and it's about 80 hertz. If you look at the frequency there, it tells you. Now let's add channel 2, which is going to be pin 11. And you can see it is exactly double the speed of the frequency of the pin 9. So that's going to be 160 hertz. And then when we add the third one, you can see it's about double that one. So essentially we have 320 hertz there roughly. Now when we add the ramp signal, you can see it's positive going right now, and you can see it syncs up to that last, to the falling edge of that yellow signal. So let's turn these back off here for a minute. So you can see where it synchronizes on the leading and falling edge. So every, what is it, 1, 2, 3, 4 pulses, this one triggers. Every 2 pulses, this one triggers. See, 1, 2. And then every 4 pulses, 1, 2, 3, 4 pulses, this one triggers. So you can see how that works. Or every pulse, I'm sorry, every pulse, this one triggers. So you have, this triggers every pulse, the blue trace every 2 pulses, and the yellow trace every 4 pulses. Now those are what's going to generate your steps. Let's take a look why. So you look, as each one of these comes in, it brings its associated current source in with it. So because sometimes one of these is low and other times they're high, what's happening is it's actually making that step generator. So you only have 3 different current sources, but you actually have more than that. You have 8 because of those pulses. Different combinations that you can bring these in either together or apart or individually or whatever. So after looking at the waveforms and kind of seeing how this thing works, it leaves us with the question yet. I mean, you can kind of figure it out by looking at the waveforms, but it's not entirely clear. How do you get 8 steps out of only 3 different lines here? Because remember, you have Q1, Q2, and Q3, 3 sets of current limiting resistors, and this is for the low power, this is for the high power, but you only use, there's only 3 different legs here, the 3 different outputs. So how am I getting 3 outputs, and how are these numbers turning out to be, where are we at? These numbers right here. Like, how do you get 24 microamps, 48 microamps, and so forth? Well, hopefully we can figure that out by looking at this little chart that I drew. So the first thing we have to look at is, I'll try to get this all in frame. The first thing we have to look at is the rail voltage on this. You're only going to use one side or the other depending on whether it's an NPN or a PNP transistor. So really the rail is only going to swing one direction. And you have a 6.2 volt regulated supply. And that's coming from here, that's why it's so important that this is so accurate. And that's why I don't like this design with these parallel diodes, but we'll get more into that later in the video. If you take that 6.2 volts, you're going to lose about 200 millivolts in this circuit. So by the coming out of this line right here, you're going to have somewhere around 6 volts. We're just going to call it 6 volts. And that's this right here. So the 4024 IC is going to eat up 2/10 of that 6.2 volt rail. Or negative, if you're looking at the PNP side of it. You're then going to go through one of these steering diodes, and these are 1N4148s, and they're going to have somewhere around 600 millivolt forward voltage drop. And your transistor that you put in there under test, the VBE, or the voltage drop from the base to the emitter, is going to be an additional diode drop of about 600 millivolts. So let's say that's a total of 600 plus 600 is 1.2 volts in the diode and the VBE. Because remember, this is directly driving the base of the transistor. And the base finds its ground through this 1 ohm resistor to ground. So that voltage drop on that 1 ohm resistor, in theory, is going to be about 4.8 volts. All right? That's all things being, nothing else being in there. Now, so we know we have 4.8 volts working here after the diode drops. On Q1, so that's your first one, when the clock kicks on and Q1 goes high, it's going to put 6 volts here. That 6 volts is going to go through these two 100K resistors that are in series. So that's 200,000 ohms. So 200,000 ohms, and remember the 4.8 volts we're talking is including these voltage drops, right? Or subtracting them. If you take 200,000, you take the 4.8 volts, divide it by the 200K ohms, you get 0.000024 or 24 microamps. And lo and behold, look at the first step above the 0 line. So there's one sweep that gives you 0 microamps where it's open. So there's your first one. If you take the next one kicks on, so this one turns off, this one turns on, you have 100,000 ohms. 4.8 volts divided by 100,000, 48 microamps. And look, sure enough, what the next step is, 48 microamps. If you take that 4.8 volts divided by 50K, because now we have two 100Ks in parallel, so that equals 50,000 ohms, you get 96 microamps. How about that? Now, where do we get these last three, you wonder? Well, here's how it goes. And if you look back up the video, you'll be able to see those square waves when they turn on and overlap with one another. Those are actually showing you when each of these lines is enabled. And the way they overlap, step 1, there's no signal, so you have 0 volts. Step 2, you only have Q1. Step 3, you only have Q2. Q1 goes off, so that's 48. Step 4 is Q3, which is 72, or Q1 plus Q2 is 72 microamps. So it just goes, it's kind of like a binary counting thing. You have 1, then this and this, which equals this, then this and this, which equals this. So you see that? So Q3, then Q3 plus Q1, which equals 120, then Q3 plus Q2, which is 144, then Q3, Q2, and Q1, which is your 168. And then the whole cycle repeats itself. So you just have those 3 lined up square waves that are all different, different frequencies. And they overlap one another, and this is what you're getting. So it's just a counter and it's just going around and around and around over and over again with that. That's how you're getting it. Okay, here's the finished schematic. And as you can see, I've made the changes on it from the original one. And there weren't very many changes made. The first thing I did was I removed those half-watt 6.2s that were in parallel. And as I said, I put a 6.2 volt 1 watt Zener diode in its place. And I mounted it way up off the board so that we have the actual leads of the diode as heat sinks. And believe it or not, when it is diode like this is rated for 1 watt, it's 1 watt including the leads. It's using the leads as a heat sink. If you cut those leads really, really short, it reduces the maximum power rating of that device. So what I did was, again, I kind of looped those leads up and mounted it up about 1/2 inch or a little over 1 centimeter off the board. And that takes care of not having those two diodes in parallel. We talked about that earlier. The other thing I did was I made the scaling circuit. So I left this one intact, and you can see that up here where it says 1 volt equals 1 milliamp. But then I added this second one using a simple little op-amp circuit. Now here's the problem. You can't just use any op-amp. And any 5532 will work somewhat, but you'll get some funny looking traces because the slew rate isn't high enough even on that. So you're going to need a kind of an instrument grade op-amp. Instead of a $1 op-amp, you're going to need closer to a like a $5 or $10 op-amp. Right now, which is working pretty good, I have an OPA, what is it? I have an OPA 2134 PA. So this is an OPA 2134. That's only in there temporarily because I actually have to get, I have a better one on order. It's an audio preamp, op-amp, but it doesn't know that it's not an audio circuit. Audio is just that's a marketing thing. The point is the gain bandwidth product is a lot higher and the slew rate is higher than an NE 5532, and that slew rate is where all the importance is. If the slew rate is too slow on this chip, what's going to happen is when those traces go up, they trace back down as it recycles. And you'll see like a loop that'll go around on your trace, and it'll just make it look bad. I mean, you can still read it, but the end of the trace won't have a nice point or a tip at the end. It'll have like a loop. So you want this to be, a fast enough op-amp. So you need a pretty good op-amp in there to do that. Another thing is, this is kind of a noisy circuit a little bit. There is a Zabel network that's on the, the voltage ramp circuit for the collector. You can see this 10 ohm and this 220 nanofarad capacitor, but you're still going to get a little bit of noise out of the transistor and out of the circuit, out of this y-axis. And when we amplify that 10 times to make the 10 millivolts equals 1 milliamp scale, you're going to amplify that noise as well. So we want to filter out any high frequency oscillations or ringing or anything like that. So this is a basic non-inverting op-amp, and even a non-inverting op-amp on top of that is noisier than the inverting op-amp because of the way the circuitry of an op-amp is designed, but I'm not going to get into that on this video. But anyway, in order to filter that noise out, I have, first of all, to set the scale perfectly, I used standard value resistors. So I used 180K for the feedback resistor. Then I used two 39K resistors in parallel. So that's going to give me, around 16K, or around 18K, 18.5K, something like that. And then I put a 2K pot in series with that. And that will allow me to adjust the feedback to get exactly, or adjust this to get exactly my 10:1 ratio. So that's what this is for. But if you notice the feedback resistor, this 180K, I shunted a 15 picofarad NP0 capacitor across that. And what that's going to do is, if this is not on there, you'll see the little ripply noise. It really, you can still read the trace, it doesn't hurt anything, but it drives me insane to see those little oscillations on the traces. This takes it completely out. Strangely enough, if you put a 10 picofarad, it's not quite enough. You can still see a tiny amount. If you go to the next size up, which is a 22 picofarad, it actually starts to affect the traces at the tip of the trace. They kind of Y off a little bit like that. So this actually was just like the perfect capacitor for this. It filtered it out perfectly. That's why that's in there. and then you can see it goes to another jack. So you have two connectors. You can connect it direct, or you could connect it to the 10 millivolts equals 1 milliamp, and that kind of amplifies the signal. So if you have a transistor that's for instance, very low gain or something like that, where the traces are going to be very small, a lot of times that gets you down in the noise floor of your oscilloscope, of the input of the circuit of your scope, and you get a noisy looking trace. This gets rid of that, because now you can, if you're normally going to be at 10 millivolts per division, you're now at 100 millivolts per division, and you're well above the noise floor of your scope. So you get a nice clean trace. That's why I did that. So that's most of the improvements that I did on this. And I did some neat wiring and so forth. And then last but not least, I just put a 4P DT switch, which is here with center off. And 3 of those poles are for the emitter base collector to switch between this socket and this socket. And that 4th pole that was left over is to allow the drive, the voltage for these LEDs, so you can see which socket is active. So if I turn this one on, you can see it lights up. And if I turn this one on, it lights up. So that allows us to very easily compare 2 transistors. And if we look up here, I have my mixed domain scope, which is really cool because you can actually look at the waveforms of each channel up here in this little strip bar up here, and you can look at the XY axis there. And if I go to transistor number 1, there's your traces. And if I go to transistor 2, there they are. And you can see this is a perfectly matched pair, at least gain matched pair of transistors. See that? They're very close. There you go. And in order to measure that, you're just going to measure your voltage up here, which is right now we're at 100 millivolts per division. So 100, 200, 300, 400, 500, and there's about 530. So taking that into account, we take 530 millivolts. And remember, we're at 10 millivolts equals 1 milliamp, so 53 milliamps. Okay, so there's 53 milliamps divided by 0.168, which is 168 microamps. And your gain is about 315.4. And remember, that's with 168 microamps of base current. This is a lower amount of base current, so it's going to be a little bit higher. It's probably closer to 150 or something. But you can see it's saying it's a gain of 378. So from 315 to 378, that's pretty close. And again, this is going to be lower because that base current. And if conversely, if we go to one of the other steps, like let's go to the 144 step. So here's the 144 microamp base current step. And that's going to be 10, 20, 30, 40, or I'm sorry, 100, 200, 300, 400, 500. And right there's about, not quite 500, it's about 480, let's say. So that would be 48 milliamps. 48 milliamps divided by 0.144 is 333, and you can see it goes up from there. So each step is going to have a little higher gain than the other, all the lower steps. And that just shows that this uses a much lower base current to do the test than this one does. So a lot of people say this kit is no good because it doesn't have enough current. But actually, for small signal transistors, it does a much better job than one of these would ever do. And it lets you look at each of the traces and kind of see if there's any problems. You can see the early effect of the transistor. See there? We really aren't, we're beyond the early effect here on these traces, but you can see as you go up higher in these traces, this is the early effect of the transistor. So they'll start straightening out. If we had a higher voltage than that, 10 volts or so that we're putting out, and ran this up to 20 volts. Remember, this is a 120 volt capable device, this transistor. It would straighten out, at the higher gain levels as well. So a lot can be learned about a transistor using this cheap, simple little kit. So just one final peek at the inside. It's nothing special. The power transformer's here. The power supply board is mounted here. I put this little standoff with this resistor, and it's just a 1K, or what is it, a 4K resistor, 4.7K resistor, and that's just the dropping resistor for those little LEDs. There's your 4PDT switch for the sockets to select the two sockets. And you can see I just wired up those sockets on a little proto board. And then these are the switches for the NPN, PNP, high power and low power modes. There's another little board down there that holds the op amp for the scaling circuit, and there's the pot to adjust it, to calibrate it. There's your the main circuit board for the curve tracer right there. These are the driver transistors. These are the two ICs that are in there, the TL074 and the 4024. Here's the precision resistor that I added because, again, I put a note on there on the final version. Where is it? That it's 1 ohm, 2 watt, and actually this one's a 2.5 watt at 0.1%. Now, why is that 2 watt? Why did I raise it from a half watt to 2 watt? Well, in theory, if you have a high enough gain transistor and you switch this thing over to the high power mode, you could actually have up to, I mean, in theory anyway, as much as almost 1 amp, So 1 amp, 1 volt, or I'm sorry, 1 volt, which would be 1 amp. So 1 volt over 1 ohm is 1 amp, and that would be 1 watt. And of course, you drive a half watt resistor to 1 watt, that would not be good. So, and this is a 0.1%, because, all your measurements are taken across the voltage drop of this. So there it is. Now, one last note about this you have to remember. When we calculated this out, we're assuming that the forward voltage drop is 0.6 or 600 millivolts. You know that every diode and every transistor is slightly different. So those voltage drops will vary just, by a couple of millivolts here and there. And so these round numbers may not be perfect. But if you use those numbers, you're going to be so close that that's not going to matter. And you saw that when we kind of compared it to the little tester. It's in the ballpark. And when you're doing transistor beta, you don't have to be exact. If it's got a beta of 400 and you calculate it to be 390 or 410 or something like that, it's really not going to make any difference in the circuit that you're using it in. So you're really just trying to find out roughly what the gain is, and most importantly, it's using the same circuits for both transistors that you're comparing, so it's still relevant if they match in this circuit. And that's really what this is all about. So that's it for this video. It was a lot of fun to build, and hopefully we all learned a little bit about curve tracers in this, and we could see some of the benefits of it. I think that's it. If there's anything else I forgot to mention or anything, just mention it down in the comments section. And as always, I wish you all peace, joy, happiness, and good health in your lives. And we'll see you again with the next project real soon. Take care, everybody. Bye-bye.